students, I am Saptarshi, your electronic mentor, and I am back with the final segment of MIS, that is metal, insulator and semiconductor. Well, let us continue with the semiconductors. So we can classify semiconductors based on few parameters. They are band gap, carrier concentration and position of Fermi level. Further, the band gap is classified into two parts, that is direct band gap semiconductor and indirect band gap semiconductor. Carrier concentration is divided into intrinsic and extrinsic semiconductor, and there are two types of extrinsic semiconductor, that is N-type semiconductor and P-type semiconductor. The part of the position of Fermi level is again classified into two categories, that is degenerative semiconductor and non-degenerative semiconductor. Now let us discuss about the band gap. The band gap shows the energy difference between the top of the valence band and the bottom of the conduction band. Based on electron momentum against the wave vector k, the position of valence band and conduction band determines its type. First one is direct band gap semiconductor. In direct band gap semiconductor, the top of the valence band and the bottom of the conduction band occur at the same level of electron momentum, as we can see in this figure. In an indirect band gap semiconductor, the energy of the valence band occurs at a different value of electron momentum to the conduction band energy. Now the next discussion is carrier concentration. The number of majority carriers present per unit volume of a semiconductor is known as carrier concentration. As we can see, in p-type material the majority carrier are holes, whereas in case of n-type material the majority carriers are electrons. Now if we plot a graph between electron density and temperature, it will clearly show us the position of intrinsic and extrinsic semiconductor based on their concentration of carriers. An intrinsic semiconductor is a semiconductor in its purest form with no unpleasant dopant species present. In this type, the number of excited electrons and holes are same. Now coming to extrinsic semiconductors, it is a type of semiconductor which is doped by a specific impurity. The word doping means adding specific impurity. This process generates carriers. In this figure, we can see a free electron is generated, and due to this, it is very suitable for electronic applications such as diodes, transistor, etc. Based on doping element, the extrinsic semiconductors can be classified into N-type and P-type. Now coming to the N-type semiconductor, this type of semiconductors are extrinsic semiconductor which has been doped with electron donor atoms is called an N-type semiconductor, because the majority charge carriers in the crystal are negative electrons. And P-type semiconductors are also extrinsic semiconductors which is doped with electron acceptor atoms, and that is known as P-type semiconductor because the majority of charge carriers in the crystal are positive holes. Next topic is position of Fermi level. Fermi level is the maximum energy state which is occupied by the electrons in a material at absolute zero temperature. With an increase in temperature, the electron starts gaining energy. The Fermi level shown in this image is the maximum energy state of these electrons. Now coming to the classifications of it, we get degenerate semiconductor. It is a semiconductor with a very high level of doping that the material starts to act more like a metal than a semiconductor. For N-type material, the Fermi level of this semiconductor lies in the conduction band. Now non-degenerated semiconductors. These are also known as semiconductors whose Fermi level is at least 3 kT away from the either band edge. Now as we have come to an end of this section of MIS, let us discuss the prime identities and differences between metal, semiconductor and insulator. Now we have plotted characteristics for each of the type of this material. For conductivity, in case of metal, it is very high. For semiconductor, it's moderate. For insulator, it is low. In case of resistivity, metal is low, semiconductor is moderate, and insulator is very high. There is no forbidden gap in case of metal. In case of semiconductor, there is a small forbidden gap, and in case of insulator, there is large forbidden gap. Temperature coefficient for metal is positive. For semiconductor, it is negative, and for insulator, it is negative. Now, the large number of electrons are present for conduction in case of metal. Small number of electrons are present for conduction in case of semiconductor, and moderate number of electrons are present for conduction in insulator. The resistive value of metal is less than 10 to the power minus 5 ohm meter. In case of semiconductor, this resistive value lies between 10 to the power minus 5 to 10 to the power 5 ohm meter. And for insulator, it is more than 10 to the power 5 ohm meter. The current flow in metal happens due to free electrons. In semiconductors, current flow happens due to holes and free electrons. And in insulator, the current flow doesn't occur as there is no free electrons. Current carriers at normal temperature. In case of metal, the current carrier is very high. In case of semiconductor, it is low. And in case of insulator, this is negligible. In case of metal, the conduction and valence band are overlapped. In case of semiconductor, the bands are separated by an energy gap of 1.1 electron volt. In case of insulator, bands are separated by an energy gap of more than 1.1 electron volt. At absolute temperature, metal behaves like a superconductor. At absolute temperature, semiconductor behaves like an insulator. And an insulator is obviously behaves like an insulator. The formation of metal occurs due to the metallic bonding. The semiconductor formation occurs due to covalent bonding, and the formation of insulator formed by ionic bonding. In case of metal, there is only one valence electron in the outermost shell. In case of semiconductor, 4 valence electrons are present in the outermost shell. And in case of insulator, there are 8 valence electrons in the outermost shell. Now, the examples of metal are copper, mercury, aluminium, and silver. The example of semiconductors are germanium and silicon. And examples of insulator are wood, rubber, mica, paper, etc. With this, I would like to conclude this section of metal, insulator and semiconductors. You watch all the section of MIS, and in this class we have studied about the types of semiconductor based on band gap, types of semiconductors based on carrier concentration, types of semiconductors based on position of Fermi level. Distinguish between metal, insulator and semiconductor. Bye bye and have a nice day.